Okay, so this is a like collaboration with Broadcom, which is on the line of introducing more time cards to the ecosystem, and this is again on the same lines of having the timekeeping separated from the distribution. So the special thing I will say about this time card is the throughput, which has been considered here. But again, there are like two classes of time cards you see: the ones that they do the timekeeping alone and the like separated from the transport, and those that they combine the transport and the timekeeping. So this is among those that combines the transport and the timekeeping, and it has also some extra features that I don't want to spoil it, to leave it to Eric as he goes through it. So Eric.
Thanks, Ahmad. I'll ramble a little bit. So Broadcom has been doing timing in our switching products for 10, 15 years. We've deployed in all kinds of different scenarios, all kinds of different implementations, and we have a rich history of that. So we also have NIC cards that have timing implementations. So what we decided to do is, how would we put some of these components together and solve some problems in the industry? So I think probably the biggest thing we've learned over our years is timing is hard from a big picture perspective. It requires a lot of specialized knowledge. There's a lot of test equipment and testing that needs to get done. There's a bunch of esoteric standards you need to do, and integrating this for non-experts is a real challenge. So if you take a look at a group that has typically a very software-oriented implementation, you start talking to them about PLLs, DPLLs, and you get a lot of glazed eyes. So really what they're looking for is a prescriptive, application note way for them to implement things. So in that light, what we said is, can we take a look at maybe partitioning some of the timing features in order to make them more modular and easier to isolate? The big thing that we've looked at this is in the context of an ORAN, which is a new group that's deployed maybe 3-4 years ago, that's looking at the network between the radios in a 5G or 4G network. They have a concept called a DU, which is the one that implements parts of the radio stack. And then they have a centralized unit, and all of this piece is well standardized, and one of the biggest issues that they have is timing. They have a number of different configurations that they define in their specs. And if you look at the way this was traditionally deployed, there was a specialized switch that had all the timing infrastructure, and basically all of that's where the specialized knowledge and testing was. And if you look beyond that, it was kind of everyone was just an ordinary clock or an endpoint to it. So with the different configurations that they're looking to do, they're looking to take some of those timing pieces and put them into the DU. And what we looked at is, say, can we take some of our switching infrastructure with the timing in order to do that? So what this does is, when you put the timing on the NIC card, what it does is, again, isolates all that testing. All that testing can be done on the card, and it can be done as a very simple thing to implement. The other thing that we found is that typically high port count NICs are very specialized. If you look at NICs today, getting a NIC that has more than 4 ports is pretty rare. And many of the different topologies that we were looking at required a lot of connections to radios. So turns out we have a good switch that has lots of ports. So we take the switch, connect it to a NIC, and we can solve this problem. So really, if you look at for our applications, for an application for this is, if I take our switch, NIC, and our timing solution, put these together, and it was a great solution. So we talked about this over a number of different months. We had a lot of different customer interactions, and we said, well, why don't we try to build a prototype, put this stuff together, and see how it works. And that's what we did with this high performance timing card. So again, if you take a look at the solution space for this, which I think is applicable in the data center as well, but it really gives you the implementation of what you're looking for. You have a lot of different radio units and a lot of different antennas. And if you look at one of the biggest challenges is synchronizing multiple base stations. And that's what this does. So the split here, depending upon, is if you take a look at the L1 processing is mostly done in the RU, but there's some of that processing that's done in the DU. And really taking that timing NIC and putting it in the DU server, what that allowed us, again, to do is to isolate all the complexity around the stack, around the testing of the interactions, all that stuff was contained on the card. The other thing that it allowed us to do is, again, provide the high fan out. With the integrated GPS, obviously you could run either full timing with Sync E, or you could use assisted partial timing with assisted partial timing as part of the distribution. Holdover is really a very interesting piece here. It's really all over the map as to how much holdover you need. It's kind of like insurance. They always want more, but as you can tell from some of the pieces, as you get higher performance, holdover, the size gets bigger, cost gets more, and power becomes more of an issue. One of the things that we found integrating this on a standalone NIC is, there's the environment inside a server for a PCI slot from a cooling perspective is a lot more variable than we would see in some of our switching platforms. So we had to be really careful to make sure that we knew exactly where this was being placed so that we could do that. All right, so I will not go through this, but what this here is just gives you an idea of how complicated the software stack is. And I'll probably point at two different things. There's lots of different pieces that need timing in the DU. They have a lot of different requirements from a synchronization perspective. But if you look at the DU software, it has an order of magnitude less synchronization requirements than the radio synchronization. So it's a lot easier to meet. So what we did is took the hard timing piece, which is synchronizing the individual radios. We put that down on the NIC, and we allowed that to be running independent of any load or any software, context switching, all the stuff that runs up on the host is unaffected by the radio timing that goes between the different radios. And what happens is because there's a boundary clock logically on the NIC card, effectively the DU software just peers to that local boundary clock. And what that allows the software vendors to do is integrate into a very common environment. And also, because the timing for that level of software was much less, it was a much easier integration story than having to put a full servo and all the other pieces that run up on the host and be able to do this. That's just give you an idea of what it looks like. And at this point, I think what I'll do is hold off to Ahmad to talk about the timing stack.
Thanks, Eric. So, as Eric mentioned, BroadPTP timing solution is inherent part of this NIC card solution. And BroadPTP is a full turnkey software-based solution. It provides all the standards compliant protocols, especially for the telecom market, 75.1, 75.2, APTS, etc. And the main advantage of BroadPTP is much of it runs inside the silicon. Like most of our silicon have embedded CPUs, and BroadPTP runs inside that silicon. And that means it is essentially a hardware offloaded solution that has the dedicated CPU cycles and memory. That way, the customer will be able to realize the performance that we tested in our lab. Right? If you were to do it in a host CPU, then the timing process need to share the resources with other processes, and the performance becomes unpredictable. So that's a key advantage of BroadPTP. And the other thing is we developed this for a while, and it is a very mature solution. It has been deployed in a number of silicon targeted for service provider market. We have it deployed in tier 1 telecom carriers in the US and around the world. So like you have seen in the block diagram, Firelight switch is one option for this solution, and BroadPTP runs inside that Firelight switch. With that, I will hand over to Amit.
Yeah, hi. So, like Eric explained, this architecture, this design is a cooperation between two different business units in Broadcom. One of them is building switches, and the other one is building these NICs. And if you look at the block diagram, at the functionality of this card, you can identify two independent nodes that are capable of implementing synchronization functions. One of them is the switch, which provides the multi-port capabilities to this card that can implement independent synchronization function. It has obviously timestamping on every port, and it has an embedded CPU sitting next to it. And the second independent node is the host CPU, the server, together with the NIC having its own independent timestamping capabilities. So if you think about how you can allocate synchronization functionality to this architecture, there are many possibilities, and so this block diagram, this architecture provides you with significant amounts of flexibility in the way that you can implement synchronization function. As an example, we can implement on the switch, we can implement a boundary clock, and then the host CPU together with the NIC can implement a slave clock that is attached to the boundary clock. You can use the switch to implement a telecom GM, a TGM, in which case, again, it has its own protocol stack that can run on the embedded CPU or can run on the host CPU. And in this case, it's also serving downstream nodes as well as the local node, which is one of the slaves attached to the master. And there's another option that this switch can implement a telecom transparent clock, in which case it's not terminating the protocol, right? If it's an end-to-end one-step transparent clock, it's not terminating the protocol, and it's basically acting as a fan-out TC for the single or the two-port NIC-based node. The other node, the NIC together with the host, can implement functionalities like a simple slave, which is very useful in the ORAN context, because typically, if you think of a server implementing a DU, there's significant amount of workload associated with that, and typically what you see is that a Linux PTP or PTP4L based slave clock is really all that is usually implemented in that context. So the fact that you don't have the extra workload associated with maintaining a boundary clock or a telecom GM is very useful in this context. Alternatively, you can put more functionality if you have the horsepower on the host CPU and have it implement the protocol stack for the boundary clock or protocol stack for the telecom GM. So all of these functionalities can be available either with the BroadPTP stack that Bhaskar mentioned, or standard Linux PTP like PTP4L that can run on either one of these nodes.
Thanks, Amit. So just so we know, it wasn't actually a paper design. We actually built a card, and I actually forgot to bring it. So it's my fault. So all I have is pictures, It was on my desk, and it didn't make it to my. So we built a number of these cards for prototypes internally. We did a bunch of software on it to prove out the concept, and just to hammer home exactly what it looked like. You can see that we had an onboard GPS. It was a U-block GPS, which is pretty standard for these type of applications. Antenna, obviously, and then we had on the top part is a Broadcom switch. You got all the ports out front, and you can see, with the PCIe form factor, the front panel real estate was a real challenge on this. So the front panel has effectively the GPS antenna. It has 2 QSFP interfaces, and you can use breakout cards to get, or breakout cables, to get to more ports. And we also had SFP DD modules in order to get additional ports to that interface as well. We have the Broadcom NIC is on the bottom. This is a by 16 card. It supports full 200 gig of traffic up into the host, Gen 4. We had a small control plane CPU, which is unfortunately not a Raspberry Pi, but it's a close relative of Raspberry Pi. It's a quad-core A53 small embedded core that was actually running Linux, and it was running the initialization infrastructure to get the switch up and to get the BroadPTP stack running. It also had a netlink interface up to the host, and that's how we did we used the ORAN Yang model in order to actually configure this device. And then on the top of it, we had the timing infrastructure, which is, we had a telecom PLL, which we used our friends from IDT. They were a great partner on this. And we had an OCXO from SciTime as the main option. So very dense card. So it is possible, but it is challenging. But what it did do is prove this concept out, and I do think that this is a really interesting way to go going forward. So I think that's it. What do we have on the next slide? Okay, conclusions. So I think big picture, there's a lot of moving parts to pull this off. I think we all know that. It takes a lot longer to test things than everyone thinks. And the PCI form factors, I think we talked about it, this has a real challenge with large port core bounds. This is one of the things we've had some discussions. You can go double wide, you can do a lot of different things, but there's really no good solution. I think was mentioned in the previous speaker, the PCIe slots in these embedded servers are at a premium. So consuming any more real estate than necessary is a real challenge. So one of the real use cases for this was, okay, I can have a single card slot that has my fan-out switch, large port count, and my timing. So that was a real advantage. Anyone want to add anything else? Okay, questions?
Any PTM support?
Yes.
In the future?
So, good question. So, the Broadcom NIC does support PTM. We've had it for a while. We've had some challenges getting platforms to test it on. And what we do have is we have a hardware interface between the Broadcom switch and the Broadcom NIC, so we can export the timing either by running PTP up on the host, or you could use something more simple like PHC to sys, or something less weight, because we can just lock the time base to that. So we do support that. One other thing about a challenge about the PCIe form factor is PTM is a great solution, but there's really no way to export PPS or any kind of clocking information onto the connector. There's a bunch of proprietary stuff. So as a timing community, it would be really good if we could figure out a way to get timing information, like PPS, real clocks onto that pinout. And I think as a community, if we pushed it, it may happen. But it's really a challenge until we broadly deploy PTM and get it to really work. Synchronizing multiple clocks, multiple cards, requires cables that go between them. Any other questions?
I missed the first part. I was a little bit late. So have you ever talked about the deployment set for this type of things? Are you going to targeting for like a far edge? That's going to be under the cell set?
So what we targeted this design for was O-RAN front haul network to DU. That was the use case that we primarily looked at. I think there's other applications in data centers and other places, but that was what we specifically designed it for. So effectively, what this card would do would plug into a DU, and it would provide the high fan out connectivity to the radios, and it will also provide the timing infrastructure.
Sorry about that. Follow-up question. Since you mentioned about to put on the DU, and if you make it like a run of some cloud server that's going to be deployed on the harsh environment. So have you ever talked about that?
Yes. So this card was designed to support, I think it's -5 to 85. I don't. It's just the -5 is the key one in order to be deployed in a I'll call it not full industrial, but that was what it turns out, as you go -5 and below, the cost increases dramatically for the components and mostly the passive as well. Believe it or not, become really expensive. So the design choice we made was, okay, we'll stick at -5. Some more customers thought it was a reasonable design point, so that's kind of what we prototyped it at.
Hey, Eric, thank you for that. It was interesting.
Great.
2 questions.
Sure.
Any rough estimations for power?
So this was 50 watts total.
Max.
Total max, it would fit in a single slot, non-GPU style power supply connector.
Awesome.
So yeah, that was another big consideration.
And I see an eclectic collection of connectors.
Yes.
Thoughts around that?
So that was one of the things around being able to export these across the PCI interface. If you look at the top, we have the full complement of PPS in, PPS out, and 10 megahertz in, 10 megahertz out, so is what you would expect. So unfortunately, you just run out of real estate. It's just that simple. So what we had was a card that plugged, a faceplate that plugged in next to this. So if you really needed those to a front panel, you could cable them out. It's definitely a suboptimal solution, but really I think the only practical one. We've had in the industry some initiatives to come up with a single wire synchronization, PPS, time of day. There's a couple proprietary solutions. It'd be great if we could come up with one that we all agreed with so that we could run one wire between them and get all the information that's needed.
Makes sense. Thanks.
Thanks, guys. Good presentation. Not so much a question, maybe just add context to support what you're doing. There are many factors pacing the rollout of O-RAN, a lot of challenges. But one that is widely talked about is the DU hardware. Fitting more ports and getting more horsepower in the DU. The DU has a lot to do. You see an accelerator in the design concept. So just sharing the context that is one of the factors, and that is what's driving you guys to put more ports, because if you need a huge amount of hardware for your DU, one of the benefits of O-RAN goes away, which is
exactly.
The cost saving. So
yeah.
just adding context.
Yep, great, thank you. We agree. The real value proposition is if you can implement this in a near commodity server, and I'll call it near because I don't think anyone is just taking a standard server with no modifications and using it. But you want to use a near commodity server with off-the-shelf hardware and software. And the software stack is actually fairly complicated. If you look at the way it's typically deployed today, it's Kubernetes, and depending, it can be even virtualized Kubernetes. But when that really matures, it's going to be a game changer for the operators to be able to deploy and manage these type of applications.
Yeah. First of all, it's so impressed. So Broadcom plus Meta, 2 eagles and converting into the dragon. So powerful. Impressed. I just have some comments and also the question. Because when I look at this architecture, actually it's really too powerful, the components. One is a very powerful NIC Broadcom has. Another one is the switch, also powerful from the Broadcom. But from the application aspect, is that sufficient enough with the high, basically like high port density NIC card, which is very easy for the Broadcom's chip, the chipset basically expanded, doing this job instead of you adding additional switch, powerful switch, and formalize.
So it's an interesting question. So as from a NIC player, adding more ports to the NIC is expensive, absolutely. And unfortunately, it's typically done for a very small portion of the market. So if you look at if you looked at the distribution of port counts from NICs to pretty much 1 and 2 ports, vast majority of the NICs, probably well over 85% of the market. There are some 4-port NICs, particularly for 25 gig, that did get some traction. But after that, it's almost all, and it's unfortunately not free from a silicon perspective. The other problem is you know, it's not like we want to go to 5 or 6. You want 12, and they want more. And you know, because of the switching aspect, we can add that fairly inexpensively to the solution from a total perspective. So one other thing that is interesting here is the choice, and we made a choice that I would not make again, is how do you reflect these ports to the host? Okay, do they look like different physical functions? That's the choice that we made. Turns out software is really complicated. So if we were to do this again, and what I would recommend is have the switch be a switch. Turns out it's really good at being a switch. And really have a single port that comes up and use the Ethernet switching infrastructure that's in the kernel to control the switch. I think that would be a much better solution than the one that we came up with. It was really, really complicated from a software perspective and a partitioning perspective on the board.
Yeah, really appreciate your frankness. Thank you.
I have a follow-up question regarding the one for your decision on that one. Will the split between RU-DU, like option 7.1, 7.2, 3, make you do this decision? Thank you.
So I think the big question from the different splits is the bandwidth. I mean, Amit, is there any other than that, it's really the bandwidth that's required from
and also processing. Otherwise, you have to offload lots of things to your NIC card.
Correct. So there's no offload of any of the L1 processing on the NIC card. It's literally, it's eCPRI that comes in, eCPRI is terminated. Excuse me, and if you look at the architectures that many of the DUs are looking at, is they have a standalone card that does the L1 acceleration. That's kind of the state of the art.
This card does not do any L1, sorry. This card does not do any L1 acceleration in the sense that ORAN is contemplating, right? We don't do any split L1 processing or any of that. This is not to say that it doesn't make sense to do it, right? If you can combine the DU as a bump on the wire L1 processing, it makes a lot of sense to combine that with these kind of timing capabilities. But this version of the hardware does not do that.